Good. Okay, let's continue from the yesterday. Uh, okay, couple of things. First, thank you for being here. So it seems that we lost half of the students for somewhere. Anyways, I already updated also this scoreboard, and that R there actually means okay, there. That R means that the return. So you have returned the exercises. And also, if you don't see your name there, you haven't then enrolled using that form yet. But I think everyone is now enrolled using the system. Yeah, so I will be at some point today taking a look at the what you have returned. But yesterday, when I kind of came over and looked at over your shoulders, I didn't see any big mistakes there, and I'm really happy about seeing this one this morning. So you have actually figured out how to calculate the decibels, and it seems that you have been teaching each others here. Excellent, 2 thumbs up. Keep it going. So it's part of engineering. Okay, the next. Okay, yesterday was basically how to produce signals, which is kind of one practical skill when you are working on this kind of the Octave or MATLAB kind of environment. Today we are actually going into a little bit heavy stuff, but I promise you that this is the heaviest as it gets on this course. The rest of those remaining 3 topics are more or less based on what we are going through today. So this is the fundamental part of how the digital systems actually are formed in Octave environment, or actually how they are formed overall. Okay, so let's see. I didn't have that open yet. Let me open the slideshow, and then I also want to change this one. So, digital system fundamentals is today's topic. Couple words. So, fundamentally, those are almost all operations what you ever need in digital signal processing systems. There are also some say more fancy stuff, and there is also operation called time reverse, but there's nothing fancy about it. But most of the systems, or at least the subsystems, are formed using those four operations. So there's an addition, which means simply mathematically it's add 2 numbers together or sum multiple numbers together with the sign. So there's no subtraction. Subtraction is simply addition with the sign. So that makes life easier. So basically the math symbols are on the middle row, and then this is the important block diagram symbol. So block diagram or flow chart is the term. What is it? It is in Japanese, the flow block diagram. It's block diagram. Oh, okay. Hey, I know Japanese. Block diagram. So basically, if you have an addition on block diagram, then you have 2. Generally, you have 2 inputs. You may actually also use several inputs. Oh, that was hard to remove. Okay. But anyways, addition like this is okay. And here you basically have, if you have x1 n and x2 n, then you would have the output is here x1 n plus x2n. See, this is very simple. You may actually have multiple inputs, but in reality, there are not too many processors that can actually handle more than 2 inputs at the time. So the best processors actually do it so that they can pipeline the command such that it first takes 2 values, and while still calculating, it fetches the next value. But anyways, the calculations are done actually by adding 2 values together. But this is okay for block diagram. The operator in digital signal processing is scaling. Okay, what is scaling in Japanese? Yeah, the multiply by scalar. Yeah, so scalar product. Oh, okay. Hey, I know more Japanese. Okay, good. So if you have you need to do multiplication or scaling a signal, basically that's the same as, well, let's do the same conversion as there. So basically, if you have a signal xn going into this scaling block with a scaling factor of a, what comes out is simply a times x of n. Just a reminder, this cannot be a variable. Well, it can, then it's variable gain, but it cannot be a signal. No signal. Since for signals we have multiply. So that's actually multiplying 2 signals together. Kind of a mixture. Well, that's the multiplication, and that's basically the sign, general sign for mixing signals. For example, if you have taken the radio frequency design labs, they basically have this sign for mixing 2 signals. Okay, so if we have 2 signals x and let me put it this way, yn going into multiplication, the output is actually multiplication of those 2. Never mix those. This is this is basically a scalar or a changing variable. Here we have signals. Signals can be thought that, okay, anything can go in, so they are random. All right, so then we have this time delay. Delay operation, and basically there are 2 different signs for it. One is the z to minus k. Another one is, well, delay. Oh, well. Okay, let's make it this way. Z to minus 1 is exactly the same as just d, like delay, and z to minus k is k times delay, or sometimes actually it's delay d to the power of k. Okay, so those are the same, and simply if you have x of n coming in, then that would be x n minus 1. All right. So there's also the reverse operation of delay. It's called advance operation, which is basically time shift to other direction, meaning that you are kind of taking advanced information. Sometimes, well, basically for real-time systems, advanced operation in principle cannot be, but in subsystems you can actually describe and show a subsystem easier way if you use advanced operation. Instead of delaying the other line, you will actually advance another line. Of course, the total system delay must be always so that it doesn't have a forecasting property. Okay, so those are the basic DSP operations. Most of the subsystems can be described like that one. For example, if you are building a digital control system, controlling system, they will be, you can build it using those. Okay, so have you gone through all that kind of stuff on math? Good. So this is just a review. Oh, it is fresh on your mind then. Excellent, excellent. So I'm not paying too much attention on the theory then. So basically linearity, simply, you can then apply superposition principle. So some of the input signals actually produces also the sum of the effects in output. Okay, that's a nice property of a system. Then you basically can analyze this system behavior using a very simple method by just checking what is the impulse response. Since after the impulse response analysis, you can then basically apply that one to any signal. Okay, nice property, linearity. Not totally necessary. For example, there are unlinear systems which are very useful. For example, median filtering. Very non-linear, but used a lot, especially in image processing. Okay, causality. Okay, causality means that the system does not forecast, doesn't have the forecasting properties. So there's action after, the reaction happens after the impulse. Okay. People are non-causal. They can forecast the future, they can act before necessary. Okay. And again, this is not a good or bad, this kind of thing. It's more about the does a system have a forecasting property or not. Stability. Okay. In this digital signal processing, we are calling, we are actually more interested about the bounded input, bounded output BIBO stability. So basically, if you have an input in some range, for example, your A to D converter gives values in between the 0 and the maximum value, then basically this, if the system is stable, it means that whatever the input of your A to D converter is, the output of the system also remains in some bounded values. So basically you don't divide by 0. So that's probably the most common reason for digital system to be unstable, because of sometimes you may end up dividing by 0. Okay. Next one, well, the stability is actually very good property. The system that is usable should be either stable or critically stable. Oscillators are critically stable systems. Okay, and then the last one, time shift invariance, meaning that system behavior does not depend on time. So system properties don't change. Just like a vending machine. So every time you put 80 yen on the vending machine, you can buy that one. it's nice property on vending machine, this time shift invariant, since I don't want to pay 200 or 2,000 for one bottle. Okay. Yeah, but buying gas from gas station pumps are not time shift invariant. The gas, at least in Finland, the price of the gasoline is changing every day, a little bit, few cents in here, maybe few yens every day. How would you know? You don't have cars. Sorry. But anyway, so the prices, the prices basically on sale items, that's not time shift invariant. But and okay, time shift invariance is again not about good or bad. People in general are not time shift invariant because we change our minds. Okay, and that's okay. That makes life interesting, unpredictable. Yes.
Could you give me a few seconds?
Yes. Thank you. Excellent. Co-teaching. All right. Okay. In most of the cases, at least in the case of linear filters, most common filters, when you're really interested about the filterings on the spectral space, basically we have the difference equation which describes the whole system. Okay, and generally if a system is a linear time shift invariant, meaning LTI system, basically this gives the relationship between output and input. Okay, are you using the same, since I have seen, say, on different sequence in different kind of practices, what are these characteristic terms here? Is this familiar? Hopefully. Okay. So, but anyways, when you have this difference equation, it also then it's very easy to find what is the transfer function, since you have exactly the same same values of these. Or the system parameters are also shown in the transfer function. Okay. If you want to calculate the output, difference equation is showing one way of calculating it. This is mathematically totally correct, but this is not the way you would implement a digital signal processing system. But anyways, you just take the y of n out and then move the rest of that equation to the right hand side, meaning that you are subtracting this feedback from the forward input system. Okay, so that's a general way of showing the difference equation. And then this one also has the feedback. Example, maybe I should actually also the other way around. All right, that might be better. Okay, so one example is how to run a 4-point running average filter, meaning that actually you are having a data, discrete time data coming in, and you want to do some simple filtering to get rid of the noise. So you would start calculating the average or mean value for those 4 points, 4 data points, and basically calculate the output at this data would be x of 0 plus x of 1, x2, x3. Okay. And basically divided by 4. That's what it's all about. Well, actually, we'll be calculating that point. Okay. I always make the same mistake when I'm explaining it. So basically, that'll be, you can calculate that point when you have all the data, and basically then move on to the next one. You calculate the y4 from those and so on. Okay, difference equation, you can calculate it either like this or with less calculations. You subtract or use the previous average, then subtract the previous, the latest or the most distant signal out, and basically introduce a new factor there. So, for example, if you're calculating y of 4 here, you start from the previous one. You added this data point. And then you basically lost that data point. And now you have one calculation less using feedback. So don't get the or don't use this difference equation to do the system. This was easy example since we had only say 4-point running average, but think about say 100 points, which requires 99 addition operations on the say this difference equation, but if you do it with the feedback, it's the same number as in here, only 2 additions. So you speed up the system by decades. Okay. Good. More stuff. So block diagram. So now we have the difference equation is just a mathematical formula how you could do the calculations, or actually describes the terms or these system parameters. But block diagram, this is the implementation of the system. So this is basically using the block diagram symbols, the okay, that that difference equation. So basically, you take the input signal, put it through a different delay chains, then you do the multiplications, and then you do the summation. Okay, this would consume a lot of calculation power since you are doing, well, that's just a table where you save the values, 4 multiplications and three additions to get the output. Not optimal. You can already start thinking, okay, maybe I should move the this multiplication somewhere else, or yeah, like that. This is much better way of calculating the whole thing. Or then we have also this feedback system, which now requires 1 multiplication, 2 memory locations, 2 addition operations. Okay. So the block diagram actually is shows the real implementation, how it's done, how you would do the program. It's a design for program. All right. Okay, then the transfer function. Transfer function, you don't need to be worried about that. Usually people get scared when we go into the complex plane. I have no idea why is that. I have been spending my whole life in a complex plane. Still enjoying it. Yeah, sometimes it gets funny. But anyways, the transfer function actually is the system description in complex frequency domain. So, okay, if we had a continuous time systems, then you would use Laplace transform. You're familiar with that, right? On signal classes. And the most common example is here is the how to analyze an RC circle or RLC circle, which oscillates and then it has a damping oscillation. Well, you would do the Laplace transformation of your system to do the see what the transfer function would be, and then you would Laplace transform the input signal, which is usually the square wave, and see how you can match your laboratory experiment with the theory. Okay, and it does if you did everything right with some accuracy. Okay, discrete time, nothing changes except the marking. Fundamentally, we're using Z transform instead of Laplace transform, and then the test vector is not anymore the step response. We are not really interested much about the step response. We are interested about the impulse response. Since a digital domain, you can use impulse. All right. So, why we are using the impulse? A very good reason. So now, if you know this impulse response, you know how to filter the linear convolution basically between an impulse response and your input signal is the output of the system. And that actually means the Z transform of Z transform of input multiplied by Z transform of impulse response, which is transfer function. And then you invert Z that one, you get the output. But let's see. So, okay, more stuff, math stuff. This is just a reminder about the transfer functions. So Z transform properties Z transform is linear, meaning that if you have a sum of inputs, weighted sum of input, you can break the sum and take the scaling factor out. Time shift, if you have a time shift, you will actually end up having the Z2 minus K coming out of the equation. Remember, earlier I had the delay is actually same as marking with the Z2 minus 1. It comes actually from this one, 1 time step delay. And then unit impulse. Unit impulse Z transform actually comes up just number 1. Then the unit step, this is for step, the testing purposes. If you are basically having a real kind of real life system and you have a real life output on your system. For example, you want to test your own digital filter in real life. You run a test signal to it and see what comes out. Then you would probably run well, since we don't have impulse generator, we have the square step to check it. You run this test signal unit step and see what comes out. And in your digital design, you can check it with that kind of the theoretical testing. Okay. Oh wow! So if we had did I take a picture of that already? Yes, I did. Good. So it's all there. But anyways, when you have the transfer function, normally written like the wait a minute. Usually, actually, I think for some reason, the most common way of transfer function showing up a transfer function, you just describe what the system looks like in respect of current output value. You have the weighted sum of, not AK, BK times X n minus K minus, remember the sign for the convention. It came from the fact that this is originally here. K from 0 to M, AK times Z2. Not Z yet. This is still time domain. Y. So this is the feedback of the signal. Okay, this is the forward going system. Okay, maybe I also should draw a small block diagram. So the system has an input. It has the delay chain here, and so on. Then it has the B0, so the scaling factors, B2. Then it goes to sum. And that is the other term. That goes to output. But also the output has the feedback, so the previous value, the value before that, and so on. And all of these also have the scaling factors on feedback. This is A1, A2, and this actually continues that way. So that's the forward type of presentation of the block diagram for this system. Okay, this system transfer function h of z is simply you take those elements so this is a just the nth degree polynomial of z, and those are the polynomial coefficients, and then down below we have k from 0 to n, okay, again 0, so a0 is 1 in this case, and here we have ak times z2 minus k. So any linear time invariant system can be described as a difference equation like that, which automatically also defines the transfer function of the system. So these terms are exactly the same. Reminder, remember the sign here. Most common error when you are making the transfer function is forget this sign operation here. All right, but anyways, these are fundamentally, they are the same. Good. Which is good. You don't need to do any extra calculations in between. So, for example, 4-point running average filter, h of z, well, this is the hard way, but on the other hand, if we just take this and just compare, b case would be 1/4, and there will be 4 terms, okay, z to power of 0, z to power of 1, z to power of minus 2, z to power of minus 3, and all are multiplied by 1/4, okay? And then the bk is actually just a0, which is 1. So the denominator polynomial is simply 1. Okay. Or, okay. Then you can make a trick. Remember the other way of calculating the 4-point running average. If you multiply that part with 1 minus z2 minus 1, and also divide, so basically you're multiplying the whole thing by 1. This one actually product gives 1 plus z2 minus 4, while this one goes downstairs. Remember, now we actually have a, all right, see, let's put it here. So that looks like we have difference equation of yn minus yn minus 1 equals 1/4 times x of n plus x of n minus, wait a minute, sign error, minus. I found some sign error on my own notes. Excellent. So this one here is not plus, this is minus. Okay. So see, y of n equals 1/4 of x of n minus x n minus 4 plus y of n minus 1. Exactly our feedback system. So everything kind of matches up in time domain. Time domain, basically we just use intuition or actually, yeah, inductive deduction to think of how this system can be reorganized to calculate the running average faster. Here we do the same thing on basically playing with these complex polynomials. Wow. Good. If you need to, explain in Japanese, please do. Please go ahead. Okay. So yeah. So this is the next one, the zeros and poles. All right. Let's see. So we had the wait a minute. I need to change the view a bit. Maybe that one is a better view here. Okay. So basically zeros and poles. So okay. Now we have the transfer function. So we started with the difference equation. And now the next step would be the transfer function. Let me repeat again. So AKY n minus k equals to BK x n minus k. That basically is equal to the Z transform where we have the BK terms and basically this is the negative polynomial or relative polynomial z2 minus 1. Okay. How this one actually can be transferred into zeros and poles. First, we need to do some, not k, k, not n, 0 to n. Okay. First, we need to do something for that polynomial that we can solve the equation. And what we do, we will actually multiply it with z to n both polynomials on this equation. And why we are doing it? Just because it's fun, maybe, but it also has some use, but later. So basically this comes bk, k, ak, z2 minus k. When you take those in, you actually have k from 0 to n, k from 0 to n, ak, bk, z to n minus k on both. Okay, what I did is just to make sure that the exponents are here positive polynomials. Then we can actually, this is exactly the same as, let's see, highest polynomial, actually b0 times z to n plus b1 times z to n minus n minus 1 plus, and so on. The last one is bn times 1. Okay. Nice polynomial. A0 times z to n plus a1 z to n minus 1 plus, and so on. So we have numerator and denominator are now in a nice form. They are both positive exponential polynomials. All right. Now, each of these polynomials have roots, the special points where this polynomial actually goes 0. So the transfer function the zeros are actually the same as the roots of this polynomial. Simple. And there's always, since we are now on complex plane, exactly n times. N roots. No less, no more. Exactly n roots. And then the poles actually are the roots of the 0 to n, ak. So that's the denominator polynomial. And that one also have n roots. Okay, the amount of roots, this n here and n there could be different. It depends on what kind of time property you have on the system, but for the minimum delay systems, they are equal. Okay. Wow. That was fun. Those zeros are off placed. Sorry about that. Okay. So, for example, well, I was basically on my display. It looks depending on the display, those are on the different places, but that's just an artifact due to this display program. But anyways, this is the Argand's diagram, which has the real axis, imaginary axis. Poles are marked with crosses, and if you have a multiple pole or multiple 0, you will put a number, how many of them are there. Then this also plays for total gain of the system. Total gain actually is same as B0 divided by A0. That's the highest polynomial coefficient, the division, and that defines the total gain here. It's quite obvious if you basically just divide the system with this one. So basically, you will have then just parameters coming, or start from the other end. So just start the poles and think of the polynomial that comes out of it. Then basically the highest polynomial term would be 1. So basically that one will scale that one. All right, so and then the zeros. Generally, when you're talking about the filters, the zeros are put on the unit circle on the complex plane. Sorry, these are a little bit off. I should have done a better picture. And then poles for a linear system are usually, or usable system are usually inside of the unit circle. Basically, if they are outside of the unit circle poles, then we have unstable system. But that matters only about the poles. Zeros can be anywhere. It doesn't matter. So, okay, stability the other way around. How to make system output go infinite. That goes to 0. You want to avoid this polynomial at any values to go to 0. So then the only way is basically to keep those poles inside of the unit circle. That comes basically also the idea of region of convergence of a system. Okay. Yeah. Wow. What happens here? Oh, real axis, imaginary axis, unit circle, multiple pole, system gain. Okay, there. And that is an example of 4-point running average filter again. So that's the transfer function. And basically you can then, well, this has the negative index, negative polynomials, but well, we do this one here. We can see, okay, we actually have poles and they are all on the origin of the complex plane, and then we have basically this can be also divided in 2 parts. You have c plus 1 and c squared plus 1. When you multiply those together, you would get that one, which means that this polynomial z plus 1 has root in -1. This gives c squared is -1, which means that you have pole 0 at plus and minus j on imaginary axis. Ha! And yeah, we have triple pole at origin, meaning you just set z cubic z equals to 0. Good. And that's about the stability. All poles are inside of the unit circle. The system is stable. 3-point average, or actually no, 4-point average, absolutely stable. All the poles are inside. If they are outside, then the system is unstable, meaning that if you hit it with any impulse or whatever noise you may have, it usually starts oscillating really radically, and eventually it will be going to infinity, meaning in computer not a number. Your floating point unit gives you not a number, or arithmetic logic unit gives you overflow flag. Okay. And poles, if the poles are only inside and on the unit circle, that's an oscillator. That's critically stable system. The hard part is actually have it exactly on the unit circle, meaning that you always have the computing accuracy or inaccuracy on the system. And if you have even the machine epsilon off the unit circle, it may actually start little by little being on the wrong side, meaning unstable side of the system. Okay, but there are special techniques actually to how to make a almost critically stable system, meaning a stable oscillator on digital domain. Basically what you need is a gain limiting kind of system. So for stability, meaning zeros can be anywhere, inside, outside on the unit circle. Excellent. So thank you for listening. And now we have a short break. And after the short break, well, let's see, is it the lunch break actually, or short break? What time it is? Oh, yeah, we could actually start the lunch break now and continue at about 12:40 or something like that. So we have about 1 hour lunch break. Okay, good, excellent.